Okay, today we're going to discuss 1D kinematics motion with words. So we're just going to look at verbally how to show motion or discuss motion. The first term is mechanics. Mechanics is the study of the motion of objects. So any motion is going to be considered mechanics. Kinematics is how we describe this motion using words, diagrams, numbers, graphs, and equations. And kinematics is how we'll spend most of our first quarter in physics when we look at by looking at mechanics in terms of kinematics. Two terms that come up again and again during the study of physics are scalars and vectors. A scalar is a quantity that is fully described by its numerical value, or what we call a magnitude. A vector, on the other hand, is a quantity that is fully described by both a magnitude, a numerical value, and a direction. And these directions can be something as simple as up, down, left, right. They can be north, south, east, west. They can be 30 degrees north of east. So you can see they can get really specific when we talk about these directions of vectors, or they can be pretty simple. But vectors have a direction, scalars do not, and that's the main difference between those two terms. So very quickly, let's take a look at scalars and vectors. And I'm using the physics classroom, which you can get onto anytime you like and look at things. So for example, I want you to do this yourself. So I'm going to do a quick, so pause the video here and just think about what you think the answers are to these 6 items. Okay, since you've paused, let's talk about them now. So 5 meters, scalar or vector? It's a scalar because there's no direction. 30 meters per second east, again, it gives a direction, therefore it's a vector because there's a direction. 5 miles north, again, vector, because it has a direction. 20 degrees Celsius. Now, 20 degrees, we're not talking about an angle, so therefore it's a scalar, there's no direction. 256 bytes. Obviously, no direction, it's a scalar. And then 4,000 calories, which must have been my dinner tonight. It's a scalar because there's no direction listed under it. Scalars and vectors, and those terms come up again and again in math as much as we see them in physics. So, the first two terms are distance and displacement. Distance is a scalar, how much ground an object has covered during its motion. Displacement is vector, and that is how far out of place an object is. So it's the change in position of an object, where you start to where you finish, while distance is total ground covered. Displacement isn't how far you've walked, it's how far you finished from where you started. And those are two terms that come up again and again, and you have to be able to differentiate between the two. So I have some examples here. The first is let's look at this situation here of starting here, okay, and we walk this far, or I'm sorry, we walk this far, and we walk 4, then we go 2, and then we go back 4. So our distance traveled is 2 plus 4 plus 2 plus 4. So 8 and 4, right, is 12. So our distance is 12 meters. But our displacement, on the other hand, is we look at where we started and where we finished, and we start and finish at the same place, which means our displacement is 0 meters. We have not been displaced at all. So even though we've walked 12 meters, we have no displacement. So let's look at another example. Here we have the skater or skier starting at A, finishing at D. So we went all the way to here. During the first minute of skating, it's 180 meters. Then we went back to here, which was 140, so we went 180 plus 140. So 180 plus 140, 320, and then we went from here to here, which was another 100. So we went 420 meters. That 420 meters was our distance traveled. Our displacement is where we started to where we finished, which is this distance here, or 140 meters. So our displacement was 140 while our distance was 420. And lastly, guy walking along the sidelines of a football game. We start at A, finish at D. We traveled from 50 to past the goal line. So we've traveled 55 yards. That would be our displacement, but our distance would be, we went this far, then we went back, and then we went back. And you'd have to add up all those distances to get there. Displacement, distance. Displacement, total position from where we started to where we finished. Distance is how much ground we traveled. Two other terms, speed and velocity. Speed's a scalar, how fast we're moving. Velocity is a vector, the rate at which an object changes its position. So when we talk about velocity, velocity is just speed with a direction. That's what velocity is, speed with a direction. So speed tells us how fast we're moving, but velocity gives us a direction that our speed's going. So now, velocity vectors. And this is pretty easy, and I put it in words here, but if we're going to the right 5 meters per second, then our velocity vector is to the right 5 meters per second. So it's pointing in the right direction. If we're moving north, and we'll just use normal directions, and we're going north 5 meters per second. So it's just the direction the object is moving, and that'll be important when we talk about acceleration. So, average speed, distance over time, how far we travel, how long it takes to get there, average velocity, displacement over time. Okay? And that's going to be important when we look at distance versus displacement. Remember, distance is how far you've walked, how much ground you covered. Displacement is from point A to point B. So, while on vacation, Lisa Carr traveled a total distance of 440 miles. Her trip took 8 hours. What was her average speed? Again, speed is distance traveled, 440 over 8. And we do the math and we'll get our answer, which will be in miles per hour. 440 divided by 8. 4, 5, right? 5, 40, 5, 55 miles per hour. A very safe speed to travel. Two other terms that go along with speed: instantaneous speed, your speed at any given instant in time, and your average speed. It's the average of all your speeds found simply by using the distance versus time equation, distance over time equation. But instantaneous could be your speed at any given time. So it's kind of like you're driving to school and you're on the highway and you're traveling a very safe 55 miles per hour. You stop at a stop sign. Your instantaneous speed at that time is 0. And then a little bit later you take off traveling 40 because you're in town. To find your average speed, you'd have to take total distance traveled over total time it took. But your instantaneous speed at one time was 55, and then it was 0, and then it was 40. So constant speed versus changing speed. If you're moving at a constant speed, your time and position will be move the same way, right? For every 1 second you travel, your position changes 6 meters. But if we have a changing speed, you can see that it's not a very consistent change. Like for the first second, we traveled 1 meter. But in the second second, we traveled 3 more. But in the third second, we went 5 more, etc. So this object is speeding up, while this one stays at a constant speed. So, physics teacher walks 4 meters east, 2 meters south, 4 meters west, and finally 2 meters north. The entire motion lasted 24 seconds. What is the average speed and average velocity? So we start here, and we went here, 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 and here. So when we talk about speed, it's total distance traveled, which is 4 plus 2 plus 4 plus 2. So it goes 8 and 4, 12 over 24 seconds, which means we have 0.5 meters per second for my speed. Velocity, on the other hand, is displacement over time. I started here and finished here, which means my displacement is 0. And I take that over 24 seconds, and you don't have to be a math magician to know that your answer is 0 meters per second for velocity. Velocity is displacement. speed is distance. And lastly, acceleration. Acceleration is also a vector quantity that is defined as the rate at which an object changes its velocity. An object is accelerating if its velocity is changing. So, a couple things. Velocity, remember, could be speed. So anytime our speed changes, we change our velocity. Or it could be anytime we change direction. Because velocity as a vector is speed or direction. So if we change our speed, we accelerate. If we change our direction, we accelerate. So our speed can stay constant, but if we are changing direction, if we're turning, we are considered to be accelerating by the definition here of acceleration. So, accelerating objects are changing their velocity at a constant amount. If we see our velocity changing a constant amount, we have a constant velocity. If our velocity varies in its change, goes up 1, goes up 3, goes up 1, goes up 2, then we have non-constant acceleration or changing acceleration. Most acceleration we will talk about in kinematics early on will be constant acceleration. So, formula for average acceleration is change in velocity over time. Now, change in velocity. Final velocity minus initial velocity over time. This is an important equation. Final velocity minus initial velocity over time is what we call our average acceleration. Units of acceleration are units of velocity divided by time units. So it could be meters per second or meters per second squared. Or it could be miles per hour per second, or it could be kilometers per hour per second, or your meters per second squared. But it's distance / time / time. And that's what we expect to see with acceleration units. So, lastly, acceleration vectors. And here's the rule when we talk about acceleration vectors. If an object is slowing down, then its acceleration is in the opposite direction of its motion. I'll repeat that. If an object is slowing down, then its acceleration is in the opposite direction of its motion. So, here's our situation. Our velocity's going this way, and we're speeding up. If we speed up, our acceleration is going the same way. So we're speeding up. If our velocity is going this way and our acceleration is going opposite, we are slowing down. So speeding up, they go the same direction. Slowing down, they go in opposite. So another way we could be speeding up, if velocity and acceleration are both going to the left. And another way we could be slowing down is if velocity is going left and acceleration is going right. So as long as they're going in opposite directions, you're slowing down. Speeding up if they're going in the same direction. This will help you on the assignments. Ask questions if you have them. Hopefully this was clear. If not, tell me what wasn't clear and we can make some changes.